Okay. Chapter 10 problems are due today. And I didn't realize when I assigned the lab also due today, but I'd forgotten about that. So if you're pressed for time, I may not be getting to the chapter 10 problems to record the scores over the weekend. So if you need to get caught up, put that as a lower priority than your lab report. Chapter 11 will be due the Monday after we get back from Thanksgiving. So I haven't gotten a chance to put any of that on Canvas. I will. Okay. And then questions for today about whatever you have questions on.
Can we go over ranking of which bases are better, more stable, based on bulkiness? I don't know what.
Well, we only have two bases that are we only have one base that's bulky.
So we don't have to learn about in the chapter.
Well, what bases are in chapter 11?
I don't know. It was talking about bulky bases.
I don't know. Where would that be? The end of it. Okay.
Let's go, chapter 10. On 10.35.
10.35, 10.35.1.
Yeah.
Okay. Now, so one of the things that they talk about here is they introduce the idea of Hoffmann. So we've talked about whose rule is it that you form the most stable double bond? That's a Zaitsev rule. There's also a Hoffmann elimination, but the problem, I don't normally use that term. I think Dr. Kwan might use it a little bit more. The problem is that the Hoffmann reaction we'll talk about next semester. And so I can introduce the name, but the real reaction that it's named for is months away. So there is a Hoffmann product that typically is the less stable product. Or remember, we kind of modified that a little bit. It wasn't so much that it was the less stable product, but when we used tertiary butoxide, we always removed the hydrogen that was least sterically hindered, which oftentimes will give you the less stable product, but then not enough to justify saying that it does all the time. So the Hoffmann product then, what they're looking at here in terms of the bases is they're saying, okay, if we use these three alkoxides and we do this reaction, they're showing you experimental data that says you get 71% if you use ethoxide. So their ethoxide behaves like what base if it does E2? It behaves like NH2 minus because it's small. And the other thing that we'll take into account later on is the fact that this is a tertiary halide plus then a nucleophile. So the problem, and so the way this would work is, we're getting into the gray area here, but it's okay because I've sort of said this before. Tertiary halide plus strong nucleophile. What mechanism would that be? Well, it would normally be SN1 with some E1. But what happens is if the nucleophile is really strong and also a strong base, the nucleophile comes in and it tries to do SN2. Because that's really all an alkoxide can do, is to do substitution. So it comes in, it says, oh, tertiary halide, I can't do SN1. It gets angry and comes back and rips off a beta hydrogen. So if it can't do SN2, it'll come back and do E2. And in this case, it will do E2, but since it's small, it can get at both sets of hydrogens equally, and so it'll form the more stable product. Right? It's just like NH2 minus. But then when we make this too bulky, it still tries to come in and do SN2. It can't because of the bulk, and so then it says, okay, I'm going to now remove a hydrogen, but since it's bulky, it has no choice but to pull off the hydrogen that is least sterically hindered. And then if you use a super bulky base, which this is tertiary butoxide, this is 3 ethyl groups, that one's going to be even more sterically hindered, so it's going to be drawn more to removing these hydrogens because they're less sterically hindered. So the bulkier the base, the more it's going to have to remove the less sterically hindered. In our world, we have major products and minor products. So this would give the same major product, regardless of how bulky it is. Right? And so this is confusing, is what they say. Why is it confusing? Was it not said earlier that the transition state in any E2 reaction has a double bond character? Yeah. Thus, in the above example, the tri-substituted alkene-like transition state will be more stable and have a lower activation energy than the di-substituted alkene-like transition state. I think we did that, right? We talked about the idea that the transition state is what guides the reaction. So the transition state of having a bulky group getting at the more substituted hydrogen has a higher energy, and it'll be lower when it goes after the less sterically hindered hydrogen. And then when it crosses over on the other side, because one produces the more stable product or the less stable product. So they need a diagram for that. So that's what we're talking about. They're still using tertiary butoxide as their sterically hindered base. If they use ethoxide, I guess when they use ethoxide, think of it as NH2 minus. It's a small base that's not acting as a nucleophile. Of course, they're basically saying, well, this has to be with a tertiary halide, right? They're not doing secondaries, because our rules would predict secondary would be SN2, right? And we drew that diagram, not as colorfully as what's here, but we talked about that. So does that help? What else? And so we can get to the point like these problems where we can say, and I'm letting them do it, hey, you're starting with this base. I want to choose. I want to form the less the less substituted product, which when I come over here, I have two sets of beta hydrogens that I can remove. I want to remove the less sterically hindered one. Which base should I use? And it says to get the desired alkene, well, there's only two bases, sodium methoxide and sodium whatever that triethyl ethoxide is. And so you'd have to use which one? You'd have to use letter 3. So with chapter, what is this, 10? With chapter 10, we've done a lot of this. It's just they're summarizing it. We kind of summarized as we went. So it shouldn't take you too long to do chapter 10. And then Hoffmann elimination. This is the actual Hoffmann elimination reaction. Is with the nitrogen with the ammonium. So.
We go over for chapter 11.
Sure. What do you want to know about E1, SN1 versus E1?
I guess like, kind of categorizing base strength and bulky versus non-bulky because they threw in some decently that kind of complicated model, but
Do you know where?
it was towards the end of the chapter.
Substitution and elimination with primary carbons, secondary carbons, alcohols.
I think it might start at 11.
Okay, so we can go through and we can kind of summarize these. Although these, I'm not going to go in. The kinds of problems that we've been doing are what you're going to see. But basically, when you have a methyl halide, there's very little steric hindrance to that. And so that methyl halide is always going to undergo SN2. So the methyl halide's always going to undergo SN2 because there's no steric hindrance to it. You can say, but look, they took tertiary butoxide and they reacted it with a methyl bromide and they did SN2. Well, yes, because methyls are kind of a special category. There's no steric hindrance to a methyl group. So methyl groups will react with anything. Well, except water. Right down here, the last one, I see a big red X because weak nucleophile plus methyl, no reaction. Similar to our weak nucleophile plus primary halide, no reaction. So methyls are more reactive than primaries, but they still won't react with water. They still won't react with neutral nucleophiles. But they'll react with everything else. But I'm not going to give you a tertiary butoxide and a methyl halide. If I did, it would have to be SN2. So I guess that kind of violates my rule of every time you see tertiary butoxide, it's an E2, except you're seeing it in their problems, not necessarily mine. So that's the reason why methyls are just small. They will always undergo SN2, except with neutral nucleophiles. If we go to primaries now, in the molecules that they're changing, okay, so they're taking that bromide, they're taking propyl bromide and reacting it with NaSCH3. So what's that reaction? So that reaction would be all right, Na is a counter ion with a plus charge. If I take it away, it's SCH3 minus. So if the counter ions are kind of getting you messed up, erase them and put a negative charge on the other ion. Okay, so what's the product of this reaction going to be? Well, what's its mechanism going to be? Primary plus what kind of nucleophile? Strong, because it's got a negative charge. That reaction is SN2. So that means the S minus is going to come in, kick off the bromine, so that the final product will have the SCH3 where the bromine was. And that mechanism would be then an SN2 mechanism. So it's a different kind of nucleophile than what I've used, than what we've used, but it's really the same thing. If we go back, classify the electron donating group as weak base, poor nucleophile, weak base, good nucleophile, strong base, good nucleophile, strong base, poor nucleophile. What? I heard a letter. C? Will we go with C? The question is this SCH3 minus? Is SCH3 minus is it a weak base, poor nucleophile, weak base, good nucleophile, strong base, good nucleophile, or strong base, poor nucleophile? We know from our rules what kind of nucleophile is it. If it's SCH3 minus, it's strong. So then you're down to 2. So you're down to in strong, good synonyms. So now you're down to B or C. Weak base or strong base? Let's vote. So the question is, if you had to classify, here, I'll make it a more, here, I will write the question out. If you had to classify SCH3 minus, is it going to be A, a strong base, or B, a weak base? Now you may have to think about other molecules to compare it to. And since it's sulfur and our periodic table goes CNO, F, Cl, S, P, then bromine, iodine. So if we use this mini periodic table, that might be what you need to use in order to determine the SCH3 minus. Bless you. Is it a strong base or weak base? Did everybody get their answer in? Yes? You don't have anybody teleporting in from outside of class, which happened this morning. I don't know how they see the question that I'm asking for them to be able to answer it, other than if it screen captures the screen and then you see it.
It does.
Okay. All right. Just was wondering how they were getting the question. I mean, I could just see them on the side of the road or still in their jammas and, answering questions. If I just broadcast the class, then you could just stay at home. Wait, that's not a bad idea. Then I could stay at home. I'll have to get some administrative clearance on that. Okay, 19 people say A, it's a strong base. So how did you conclude that it's a strong base?
Because basicity gets stronger as you go up the periodic table. So I was thinking that sulfur is higher up the periodic table than the bromine is.
Yes, but are we really comparing yes, SH3 minus is a stronger base than bromine is. And that's, any of these we said were stronger than the halogens. So that's true. I'm thinking though in a comparison to other things. Okay, this is a weak base. Why?
Because when I think of basicity, I think of the trend like it gets stronger as you go down. And
Does basicity get strong? Does basicity get stronger as we go down the periodic table? That's not basicity. That's nucleophilicity. So as you go down the periodic table, it becomes a stronger nucleophile. But actually, what kind of base does it become? It becomes a weaker base. So as we go up, it's kind of a weaker base. But is it a truly weak base? Well, it has a negative charge, so it would fit our strong base model. And so it is a strong base because it has the negative charge. Now, it's a strong nucleophile because it has, well, no. What was I thinking? No. Strong base, anything with a negative charge doesn't, a weak base, a strong base has nothing to do with the charge per se. They all have negative charge. Give me, what's an example of a weak base?
Water.
Water's a weak base, although that's neutral. And by weak, so let's kind of draw a conclusion or a connection. Weak bases are what kind of leaving groups? Good. So what kind of leaving groups do we have? Good leaving groups do we have? Because by definition, they'll have to be weak bases. Iodide, all the halogens, chloride, bromide, suppose fluoride. Those are all basically good leaving groups. Is OH a good leaving group? No, because in order to make OH leave, we've got to protonate it first. How about an OR group? Good leaving group? Well, if OH isn't going to leave, OR isn't. Now, turn these around. What are those? They're strong bases. So If you had an SR, it would be also a strong base in that analogy. And it would be an even stronger nucleophile because S is below oxygen on the periodic table. So for this problem, you can use our rule of, okay, this is a strong nucleophile, and then it's also a strong base. Why? Because it looks like other strong bases. Would be the way to approach it.
I caught that, and I thought I was going because it has this weak
It does. Well, that was all for nothing. Why are they classifying it as a weak base, I wonder?
The answer. It gives you a little explanation.
Oh, yeah, that's true. Let's see if I buy their explanation. Where was we? We were at chapter 10, right? 11. Oh, so we're ahead. So everybody should get this one right by next week. Okay, show the correct answer, but I'm losing points. Is the charge relatively stable? Is it polarizable? Well, that's not a very good hint.
Yeah.
Is it polarizable? Yes. And that feeds into what part of the answer? Nucleophilicity. Is the charge relatively stable? Okay, the anion is stable due to the large size of sulfur, and it is also polarizable. This makes it a weak base and a good nucleophile. Yeah. We won't be doing much with sulfur at the moment, so I don't know that I necessarily. I guess the question is, where does the line between strong and weak end? And that's always a problem in acidity and basicity. So I guess I'd sort of buy that, but I still think it's a kind of a stronger base. It's stronger than it's stronger than a halogen. So I might have to go. I might have to go in, and I can go in, and I don't think I can change the answer, but I can go in and give credit for that when I look at this by after Thanksgiving. Somebody will have to remind me of that. I just randomly did that problem, didn't I? You didn't ask about it, okay. Making myself look bad. And that's still going back to this problem.
So in this class, if we see a negative charge, we should just assume it's a strong base.
Unless it's a halogen. To be honest with you, our strong bases are going to be alkoxides. Over the course of the semester, our strong bases are going to be alkoxides, and they're going to be N minuses, they're going to be O minuses, N minuses, C minuses, and H minuses. So I'm going to take that part of the periodic table on down. For the time being, I won't include S minus in that. But anything with an O minus, N minus, C minus, H minus, we're going to consider to be strong bases. And then by definition, because I just went horizontally on the periodic table, they're also going to be strong nucleophiles as well. So the question is, where does the nucleophilicity and basicity, where do those kind of break down a little bit? And we've already done the next problem, which was what mechanism was this reaction. I don't even dare want to look at the answer there because I could contemplate too. But on our rules, what would the mechanism be? I think I already wrote it out, right? SN2. What would they say? Good. They say SN2 as well. So that's what I'm saying. A lot of this is going to be and they're kind of leading you, right? So now we know what the mechanism they said this was, so now we can predict the product in the next question. So there's 79 questions. Okay. Well, you have all next week to work on them. Okay, a good review for the final, or a good review for the exam. Well, if there's just going to be one after another like this, it's going to be relatively straightforward. What else? Now, well then, I think I fixed my awkward staring limit at 30 seconds. Does anybody have other Bob?
You don't want after that where it's NaO, if the only thing that changes is an O instead of anything. It's a small thing.
Okay. So now they're going to ask you the same questions again. So now it's an OCH3 minus versus an SCH3 minus. So OCH3 minus is what kind of nucleophile? This OCH3 minus is going to be what kind of nucleophile? Strong or weak? Strong nucleophile, what kind of base? Strong base. So there's no question. It's strong for that one. And then I'm sure they're going to ask you what the mechanism is and then what the product is. So that way, if you got the sulfur ones incorrect, then you can get a hint and go to the next one. Any other questions? So here's what I want to set the stage for Monday, because we're going to start talking about alkene. We're going to start talking about addition reactions to alkenes. And we're supposed to go through chapter 13. I need to talk to Dr. Kwan if he's going to make it to alkynes. If he's not, then we'll circle back around and look at alkenes. That'll be the final chapter. And there's a lot of stuff in alkene reactions, but it's different than what we've been doing. So what have we been doing? We've been making alkenes, right? And we went through the terse butoxide, the NH2 minus with a halide, and we could go ahead and make alkenes. How did we say we made alcohol? How did we turn alcohols into alkenes? If I wanted to do this reaction, what reagent should I use? An acid? Half credit. What kind of acid?
It has to be a strong nucleophile and it's ready to count.
It's got to be an acid with what kind of counterion or what kind of conjugate base? I'll give you two choices. So what, if we want to do that reaction, should we use base A or base B? How many people say A? How about B? Okay, why B?
Will it not be able to actually attach itself to the positive charge which we're going to be creating?
Okay, so I need to use an acid that has a conjugate base that is not a
I was going to say the stable conjugate.
stable, and if it's stable, then it won't be a strong base. If it's stable, it won't be a strong base. If it's not a strong base, it won't be a strong nucleophile to be able to add to the carbocation. So our first step in that mechanism is to protonate the OH. So I'm going to take it, I'm going to add H+, but it's important that the H+ come from sulfuric or phosphoric acid with the triangle. So triangle stand for? Heat. So we need to heat this reaction. Then I'm going to protonate the OH to form an oxonium ion. Because OH cannot leave, right? It's a strong base, so it's a lousy leaving group. But if I protonate it and I make a water molecule, it's a weaker base. And so this can leave. And so then I'm going to lose my water, and then I'm going to form my carbocation. Then, if I'm going to do if I'm going to do an E reaction, I got to lose a beta hydrogen. So here's my alpha hydrogen, here's my beta hydrogens. So which hydrogen do I lose? To form the major product. Is the major product going to come from losing HA, or is the major product going to come from losing HB? HB? We all agree on that? Because then you'll form the more substituted double bond. But wait, how did I know I was forming the more stable double bond? It's the Zaitsev's rule.
Yeah.
It's Zaitsev's rule, that's true. But also because what mechanism did this reaction go by? E1 or E2? E1? We all confident in that? So what's characteristic of one mechanisms? What kind of intermediate do they have? They have a carbocation intermediate. Two mechanisms? No carbocation intermediate. So this has to be an E1 mechanism because it goes through a carbocation intermediate. So therefore, the product of this reaction is that most stable alkene. E1s always produce the more stable alkene. That is Zaitsev's rule. Zaitsev developed the rules on dehydration reactions. So what we're going to start talking about on Monday is the reverse reaction. Because when I lose my HA plus, my HB plus, to get this final product, I'm also going to have water over here. So now if I started by saying, hey, what's the product of water, alkene, and acid? What you would say is, oh, water is electrophile or nucleophile. Water's a electrophile or nucleophile? It's not a trick question. It's a nucleophile. Let's skip to the H+. What is it? Electrophile or nucleophile? Electrophile. What's a double bond? Is it electron rich or electron poor? Rich. It's rich because the pi bond is the electron richness. So I've got two nucleophiles, and so if I try and react water with an alkene, no reaction. Because two nucleophiles don't react together. I need an electrophile. So I throw in my acid as my catalyst. And so now what happens? What happens is the alkene adds an H plus to one of those two carbons. And when it does, the other carbon becomes a carbocation. So there's a reverse reaction. Then what happens to the carbocation? The water comes in and attacks it so that I form the oxonium ion. That step we've seen before. That is the second step of SN1. And then what happens? I lose an H plus to get the alcohol. So the first reaction is called dehydration. The reverse reaction is called hydration. And so what we're going to do on Monday is we're going to start adding an electrophile and a nucleophile to double bonds. And in the end, we will add an electrophile to one carbon and a nucleophile to the other carbon. There's a lot of little details in between, but that's what we're going to be doing. The second step is oftentimes the same as SN1. We're getting to the point where there's going to be a lot of review. So that's what we're going to start doing. There's a question of which carbon gets the electrophile, which carbon gets the nucleophile. That topic actually first got introduced in exam 1 on one of the problems that I gave you. We'll go back. There's going to be another rule that we'll use, which is called Markovnikov's rule. For another Russian chemist.
So would that reaction end in an equilibrium?
Yes. So actually, if I'm going to do a dehydration reaction, I have an equilibrium. And the problem is that in my overall reaction looks like this. The H plus is a catalyst. It protonated the OH, and then there was an H plus lost in the last step. So H plus is a catalyst, and we typically write the catalyst over the reaction arrow. So there's my overall equilibrium reaction. The problem here is you say, how do I get more product? You're not removing the acid, you're right, you can remove a product. You could remove the water. The acid as a catalyst isn't on either side.
Okay.
It's in the middle. It's over the arrow. So if you wanted to push the equilibrium to the right, you need to remove water as it's formed during the reaction.
By distilling?
Yeah.
Could it, would that be going the other way, trying to distill to make alcohol?
No, if you can just distill an alcohol as long as there's no acid present. You can just distill the alcohol. But what we would do is, see, the one thing we can't do is add more alcohol. Because normally when we talk about Le Chatelier's principle, it's like add more reagent. But that only works if there's 2 reagents to add. So with only 1 reagent to add, I add more alcohol. Yeah, I'll get more alkene, but I'm still going to get the same percentage of alcohol. I have to do something to remove it. So what we'd actually do is, if you could imagine setting up a distillation apparatus and putting an alcohol and an acid in there and raising the temperature of the round bottom to just below the boiling point of the alcohol, so that as the alkene is formed, since it has a lower boiling point, it distills over and leaves the alcohol behind. And if I was in a plant situation where I needed to make this, I would actually then be feeding alcohol into the, well, they don't use giant round bottoms in industry. I've only ever heard of one company that had literally a round bottom the size of this room. And I didn't see it personally. Somebody came back from a trip in graduate school and they said they have a round bottom the size of a room. And I still don't get that. But everything's stainless steel tanks. So what you would do is feed the alcohol in and capture the alkene as it comes out. So we'll have to talk about all these little minutiae of now reacting the alkenes in the reverse reaction. And that's what chapter 12 is on. So that's what we'll start with on Monday and Tuesday of next week.